Good day, everybody. Today I want to look at finding the average slope of a curve, and it's kind of well known, but that's if we take points equally spaced with respect to the x-axis, and that might not be well known. Right, so by the fundamental theorem of calculus, if I want the average value of the derivative, I will integrate the derivative, divide by the length of the interval, and we end up with the slope of the line connecting the endpoints, f of b minus f of a over b minus a. So that's well known. But again, that ends up being the average if points are taken with respect to the x-axis, say equally spaced that way. What if we took points equally spaced along the curve itself, along its arc length? Or I also did, just for fun, equally spaced vertically. Now I'm only going to look at increasing curves here, but let's see what happens. So here's a picture of the hyperbolic cosine function, and I've got 20 points equally spaced on the interval 0 to 2. You can see there's the x-axis, so 20 points equally spaced, and you can put more and more points, but you can see that there's kind of a density. They're more dense the lower the derivative is, and they're less dense the higher the derivative is. So what it's going to be, as well, it ends up just being the slope of the line connecting the endpoints. So cosh 2 minus cosh 0, which is 1, divided by 2 minus 0. So here's the average. And we can see, so if I take the 20 points, I've already got it done there. We're pretty close to that stated average. If I take more points, well, here's with 50, you can get a lot closer. Maybe go to 1,000. Right, so we're really converging to cosh 2 minus 1 all divided by 2. This is the difference of that. Looking at with respect to arc length, so here's 20 points equally spaced along the curve itself. So they're it kind of looks more uniform. But here's a picture of both the 20 points with respect to the x-axis, 20 points equally spaced along the curve, and you can see there's kind of a density of points where it's flatter when it's with respect to x, and whereas it's sort of a constant density with respect to arc length. And so it did have a higher average. If we notice the decimal value, it was 1.813, and I didn't write it down here, but it was about 1.38. So definitely higher average with respect to arc length. And if you take points equally spaced on the y-axis, that's what this is, it's going to be even a higher average. So out of those points, find the slope at those 20 points, average them. It's going to converge to this value, which is 2.1. And you can see the more points I take, the closer it gets to that average. So again, now here the density gets pushed to where it's more vertical, and where it's horizontal it won't be as dense, the number of points you pick. And it doesn't matter how many points you pick, but here's a plot with both the equally spaced on the x and equally spaced on the y. And again, so there's more points chosen where it's flatter for the x, and more points chosen where it's steeper for the y. So it's going to have a higher average, and it doesn't matter how many points you pick, it's sort of a density. So see it one more time. We can do it with a circle. There's 20 points equally spaced. The average is going to go to 1. This is a unit circle, so connecting the endpoints, the average slope should converge to 1. So if I find the slope at those 20 points, it's very close to 1. If I do it with 5,000 points, I get a little closer. And here's 20 points equally spaced along the curve. Easy to see. If I put them together, again, with the equally spaced on the x-axis, you're going to have kind of more points where it's flatter, whereas with respect to s, it's equally spaced. In this case, it diverges. The more points you pick, it's just going to grow and grow. So there's the average slope of the 20 points. There's average slope of 50 points. If I go to, say, 5,000, it takes a little bit of time here, but it can take too long. So it grows and grows. It's unbounded. And then again, if I take points equally spaced on the y-axis, so here I can partition it, you can see points equally spaced on the y-axis, then it's more dense where it's very steep, less dense where it's flat. And again, this is unbounded as well. And here's a plot of the points on the y and with respect to s. So the number of points taken equally spaced on the y-axis, it's even more on the steep side than with respect to arc length. Here it is comparing points equally spaced along x, those solid circles, and y, those hollow circles. And it turns out it's going to be unbounded. I mean, it grows faster than equally spaced with respect to arc length. So again, what we're doing is we're taking points equally spaced either with respect to x, s, or y, finding the slope at those points, averaging what we get. And then we want more and more points kind of equally spaced. And we get different values. So if I go back to the work, this first curve is 1 minus cosine of pi over 25x. We're going from 0 to 25 in x, 0 to 2 in y, so change in y over change in x is 2 over 25. So that'll be the average slope with respect to x. And we can see that. So if I take the derivative, it's just pi over 25 sine of pi over 25x, and then the average value, integrate that. It's basically back to here, except for the constant. But change in y over change in x will be what we get. Average value with respect to s is kind of hard to find x in terms of s. So we can do it with a line integral, but I'll wait on that. If I want to do it with respect to y, I need to solve for x in terms of y, which we can do, right? If I put y equal to this, I can say cosine equals 1 minus y, and solve for x, arc cosine of 1 minus y, times 25 over pi, but substitute it into the derivative. So once I solve for x in terms of y, I'll put that in to x right here. And then I can integrate this and find the average with respect to y. Pictorially, right, there's 25 points equally spaced on the x-axis. Find those slopes, average them, and it's going to converge to what we had. For 25 points equally spaced on the y-axis, so I need these 25 points, so I partition the y into 20 intervals, and it's going from 0 to 2. So, and then I took the midpoints, so it's like 1 over 40 times 2, and then 3 over 40 times 2. So the y's are equally spaced. And then since I was able to solve for x in terms of y, I can get the x value, just to plug in the y in my formula, 25 over pi arc cosine of 1 minus y. So that's how I can plot those points And then I want to find the derivative at those points. Well, the derivative is pi over 25 sine of pi over 25x. So if I put each of these x's into the derivative, that'll give me my average, and it does converge to pi squared over 100. And when we start running into the problem of, for arc length, can I get x in terms of s? Not really analytically. Right, so here's 20 points equally spaced along the curve, and I can set up an arc length function and then solve for what x value will be 1/40th of the length and 3/40th of the length, etc. So I found the x value, which would give me the appropriate length I want. So I did find the midpoint of the 20 lengths and plotted them. There's the what the average is going to be based on a line integral, and here's comparing it to the average of the slope. So 1 over pi over 25 sine of pi over 25 times those x's, which I called t inverse for crazy reason. But it is pi over 25 sine of pi over 25x, which would be what the derivative is. And I did it for those 20 points, which are the x values for these 20 points, which are equally spaced along the curve. The average slope is going to end up being 0.0801, so it's almost the same. So there wasn't much difference. You don't see it. The flatter the curve, the less you're going to see a difference between the averages. So the first examples were steep curves, like the circle and the regular hyperbolic cosine. And there you can better see the difference. So I did it for a random hyperbolic cosine curve, c cosh of x over c plus k. And in particular, so first I did it in general, and then for the specific curve, 6 cosh of x over 6 minus 6, just to put it at the origin where it starts. I went from 0 to 2. Go through too much of the work, but this is one where you can solve for x in terms of s analytically. So I could substitute it in. But I just want to focus on the results here, and again, it's increasing. So, and this is not too steep a curve, so there's not too much difference. But I do want to show our main result and how to get the average slope without having to worry about solving for x in terms of s or x in terms of y. So rather than do that, the easier thing to do is think of it as a line integral. And you can even think of a regular integral as a line integral. So the usual average value, you integrate from a to b of your function, which I want to be f prime, and you divide by the length of the interval, which will end up being integral of 1 dx. So you can think of this as a dx line integral. Anyway, so that gives the average with respect to x. With respect to s, I want to integrate f prime of x ds, and then divide by the length of the interval. ds is the square root of 1 plus f prime squared. So now I can get the average without worrying about solving for x in terms of s. And for average y, I want to integrate f prime of x dy and divide by the change in y. But this change in y is like integrating f prime dx, and in fact f prime dx is dy, because if y equals f of x, then dy is f prime of x dx. So dy becomes f prime of x dx. So we've got these three line integrals, which will give us these averages. And so now it's easy to get any average value. In fact, here's a little piece of natural log x from 1/2 to 3. And, I played around with different endpoints, but with a and b being 1/2 and 3/2 as I have above. Here's f of x, here's dx, 1 over x. And so I can do the x average. You just integrate f prime dx and divide by the integral of 1 dx. And you get log 3, which is the change in y over the change in x. For the average with respect to s, points equally spaced, here's f prime times ds, square root of 1 plus f prime squared, divided by the integral of 1 ds. And there's the exact value, but here's the decimal value, and again, it's bigger. And then the average with respect to y, is this integral of f prime squared divided by integral of f prime. And again, that's bigger. One more curve, x squared. Of course, fx squared, df is just 2x. So the average slope with respect to points equally spaced on the x-axis is 2, which is again the change in y over change in x for the endpoints. Average slope of points taken equally spaced along the curve itself, it's now almost 2.5. So that's f prime ds, square root of 1 plus f prime squared, divided by the length of the curve, which is just integral 1 ds. And if I took points equally spaced along the y, then it's even higher. So it's integral of f prime squared divided by integral of f prime, change in y. So I thought I'd offer a proof that these averages always go in that direction for increasing f. So here's the integral forms for the averages. For the proof, I changed all the f primes to f's. So just for the proof. And since my functions are increasing, f prime is always a positive function. So this is for positive valued functions. I want to show this inequality. Call it a theorem here. So first for this first inequality, if you just cross multiply, it's this term times this term. Must be smaller than this term times this term. There we go. And for this inequality, it's this term times this term right there. Must be smaller than this term times this term. So that's what I want to show. And the way I do each proof is I look at this product of integrals and I turn it into a double integral. So this is, you can just think of this as a dummy variable. So I change this f of x dx to f of y dy and change this integral of 1 dx to 1 dy. And that's what we have here. And then this integral times this integral is the same as this double integral. And similarly, this integral times this integral is the same as that double integral. Right, just the 1 is 1. And I want to show this is bigger than that. So if I subtract the two, it's this minus that has to be bigger than or equal to 0. But conveniently, they're that same square root, they have the same domain. So I can turn into a single double integral, f of x minus f of y times this square root has to be bigger than or equal to 0 over ab. Before I do the proof, we'll look, so for 2, I did the same thing. Change this to a y, and then this product of integrals will become a double integral, and change this to a y, then this product of integrals will become a double integral. There it is, right here and here. And then I need this bigger than that, so if you subtract the two, you can turn into a single double integral that I need to be greater than or equal to 0. And then for the proof on both of them, I'm going to look at all points in the interval AB, where f of x is bigger than f of y, and I'll just call that set of points E plus. And then E minus will be the set of points where f of y is bigger than f of x. And then there's also some points maybe where they're equal. I call that E sub 0. Then the important thing is, if a point is in E minus, meaning f of y is bigger than f of x, well, that means yx is in E plus. Right? So if I plug a yx in here in this order, that would mean f of y is greater than f of x. Okay, so that's the key. A point xy is in E minus if and only if yx is in E plus. And so here comes the proof. We want to show this. Well, this double integral is the integral over the E plus the E minus plus the E0. But on E0, f of x equals f of y, so you'd be integrating 0, so that's gone. And then for this double integral, I'll factor out a minus, pull out a minus, so then it becomes this. And then here's where I switch all the x's and y's and put it into E plus. So I didn't change this, but factor out a minus, and then go from E minus to E plus, switch all the x's and y's, and now I've got this integral, two double integrals, they're both over E plus, so I can make it a single double integral. They have f of x minus f of y in common, and then it would be this minus that. But on E plus, f of x is greater than f of y. So it's a positive times a positive. If f of x is greater than f of y, that's positive, that's positive. So that proves that. And for the other proof, I need this positive. So do the same thing, integrate over E plus E minus plus E0, which will be 0 if fx equals fy. So factor out a minus as before. And then to go from E minus to E plus, we'll switch all the x's and y's. So now they're two double integrals over E plus, so I can combine them into a single double integral over E plus. Again, they have f of x minus f of y in common, and then it would be this minus that. So that's what I have here. And then to simplify, think of this as a fraction divided by 1. Multiply top and bottom by its conjugate, which would be this. So the top times the conjugate, if you FOIL, outer and inner cancel, and you just are left with this minus that. Okay, so that's this numerator times this denominator gives me this numerator. And if you distribute, the fx squared, fy squareds cancel, and you're just left with this. And over E plus, fx is bigger than f of y, so that's positive, so it's positive. So that proved our result. As I mentioned earlier, if I take points equally spaced on the circle, if I do the full quarter circle here, the average with respect to s and y both diverge to infinity. So I decided to look at what if I did the average angle. So here's, this circle is actually radius 10, but so at every point, the average slope is going to diverge points equally spaced with respect to s or y. But if I look at the angle, the slope goes to infinity, but the angle goes to pi over 2, 0. So it'll definitely converge. So every angle is the arctangent of the slope. So I want to average the arctan of the slopes. If I do that for that quarter circle, then the average of the angles the slope makes with respect to x is pi over 2 minus 1. The average of the angle with respect to arc length is pi over 4, which it kind of had to be if you think about it, but I'll let you do that, because we went from pi over 2 to 0, and it's changes linearly. The slope changes linearly with respect to arc length. And then the average angle the slope makes with points equally spaced on the y-curve is 1, perhaps interestingly. One other interesting example, if I take e to the x on negative a to a, then the average angle taken with respect to x would be this average, and it ends up being pi over 4. So that was kind of interesting. So the average angle, if you take points equally spaced along the x-axis of e to the x, symmetric with respect to the y-axis, the average angle is pi over 4. Now it's probably not surprising that the average angle of points taken with respect to the x-axis is smaller than average angle of points taken with respect to arc length, which is less than or equal to the average angle of points taken with respect to the vertical y. Here we're looking at it with how I would do the proof. The proof would have f, or the average has an f prime here. Right, so arctan of f prime, arctan of f prime square root of 1 plus f prime for the ds, and arctan of f prime times dy, which is f prime dy. So all these f's should be f primes if you actually find the average of the angle. But in the proof, just to make it simple, I had f's, and then I won't redo the proof, but it's the same work. A couple lines change. The last thing I'll do is I'll compare if you find the average angle versus the average slope, and then take the angle of that average slope, which is, in other words, the arctan of the average slope versus the average of arctan of f prime. Like for the circle, the average angle ended up being about 0.5708. However, the average slope is 1, and then the angle that average slope makes is pi over 4, about 0.78. So this is a larger value. It follows from Jensen's inequality. So in other words, the average angle is given by averaging arctan of f prime. That's always going to be smaller than taking the arctan of the average slope. So I thought that was a nice use of Jensen's inequality. Here it is in full sophistication for the mathematicians out there. As a quick mention of the proof, if we wanted to do it, it's usually stated for concave up functions or convex functions, and then the inequality goes this way. So if phi is convex, a concave up function, if you did this integral where p is non-negative, then this will be smaller than that. But the inequality is reversed for concave down functions like arctan. Arctan is concave down, so the inequality gets reversed. So the arctan, and then p will be either 1 or square root of 1 plus f prime squared, or f prime, to get my averages. So the arctan of the average slope is going to be smaller than the average angle, the arctan of the slope. For this version with concave up, I followed the main line here. The main fact is a curve is always above its tangent lines, right? If you're concave up, the curve is always above its tangent line. Concave down, you'd always be below your tangent line. So probably not worth going through the proof, but just so we know, this is a fact that will always happen. Again, we kind of hinted at the reason why, but just to state it one more time, if I had points equally spaced along the x-axis, you can see you're going to have a lot more points where the curve has a small slope, near zero slope. Whereas if I take points equally spaced along the curve, I would get more points on this steep part. And even more so, if points equally spaced along the y, you'll get even more, right? If I had 20 points along the x, s, and y, the averages get higher as you go in that order. Could be clear. So that's the result. Hope you enjoyed that and this application of line integrals to finding average value of slopes. Anyway, thanks for trudging through, and hope you enjoy the rest of your day. Thanks.